Welcome, Calculus BC. This is lesson 7-2, sequences. Let's begin. So just a little bit of review. This is stuff that you might have done in Algebra 2, depending who your teacher was, but you probably forgot it because it's been 3 years. So factorials. What's a factorial? It's where we put a number with an exclamation mark. You're going to see this appear a lot in BC. Basically means multiply every number down to 1. So for example, if I had 5 factorial, that would be 5 times 4 times 3 times 2 times 1. And you multiply that, 20 times 3 is 60 times 2, that'd be 120. So this is going to be used a lot. Now, one thing we might do this for is to simplify. Now, look at this case here. So this is a very common thing to have to do with BC. N plus 2 factorial over n factorial. Well, write that out. So one way I might write n plus 2. Notice if this is plus 2, this is a little bigger. N plus 2 would be n plus 2 times n plus 1, you subtract 1, times n minus 1, and dot, 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 all the way down to times 1. And just n factorial is n times n minus 1, dot, 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 all the way down to 1. What cancels? Well, everything on the bottom cancels with most of the things on top, except these two dudes. So the answer is n plus 2 times n plus 1. So one thing to note here, yeah, you're going to have to do this kind of canceling a bunch. So, yeah. Okay, vocab words. A sequence. Last time we talked about a sequence. It's an ordered list of numbers, so there's some kind of pattern to it. A series is like where you just take that ordered list and add everything. So you're adding up all those numbers this time instead of just listing them. So here's an example. Write out the first 5 terms of a sequence. It just would be the same as first 5 terms of a series. Now, whenever you do this, you start at n equals 1. I mean, it's not kind of labeled, but you always start at n equals 1. So a sub n equals n over n plus 1. That's basically the pattern of the sequence. So you're going to do n equals 1 and the first 5 terms all the way up to 5. So term number 1 would be 1 over 1 plus 1 plus 2 over 2 plus 1 plus 3 over 3 plus 1 plus 4 over 4 plus 1 plus 5 over 5 plus 1 plus 1. And then you'd add all that up, and what does it add up to? I don't know. It's, 1/2 plus 2/3 plus 3/4 plus 4/5 plus 5/6, whatever. But you'd have to add that up. I don't want to do the math. Use a calculator. Do it at home. Write out the first 5 terms of this recursively defined. So when I say recursive is a word that we probably don't use a lot. Basically it means you use the previous term to get the next term. So in the case where we say we're going to start when usually we have to define the first term, a sub 1 is 5. A sub k plus 1 is, notice that the pattern for the formula uses a sub k. That's like the previous term. So a sub k plus 1, basically the next term is 3 times the previous term plus 4. All right, so the first 5 terms of the sequence. The first term is 5. Now the next term, a sub 2, is going to be 3 times the previous one plus 4. So 3 times 5 plus 4, I can write 3 times 5 plus 4. Okay, and you'd figure that out is 19. Okay, so my sequence, I'm going to write this down, 5 plus 19. And then the next one in the sequence would be 3 times 19 plus 4, which is, oh, this is going to be annoying. 3 times 19 is going to be 57 plus 4 is 61. And then, the next term, 3 times 61 plus 4. And 3 times 61 is going to be 183 plus 4, which is 187. And then the last term is going to be 3 times 187 plus 4, which is going to be 3 times 1. You're not going to really have to do this by hand a lot. But there we go, 565. And I could add all those numbers together. 5 plus 19 plus 61 plus 187 plus 565. And I'm going to get my answer, if I want to do the sum, that sequence, 837. There we go. We didn't have to do that, but we did. All right, recursive definition. So sometimes I'm given the pattern, and let's make the recursive pattern. So you kind of have to look at the pattern and see what's going on. So it's kind of weird. I go 2, -6, 18, -54, 162. One thing to note is it's always going plus, negative, plus, negative. So that means that pattern is doing this thing where it's multiplying by -1 to like an n power. So I'm going to say a sub n plus 1. I could use k, but I'll use n. So this thing is going to make it like kind of flip the sign every time. So I'm going to do that. And notice here that what's it doing? Usually it's like multiplying by a number or adding a number every time. So 2, 16 to 18, I'm noticing I'm times by 3. So you times them by 3 every time. Okay, so I'm taking that -1 to the n power times 3 times the previous one. So the previous one would be a sub n. So that's kind of the pattern there. And that would be a perfect recursive definition right there. So this -1 actually flips it, makes it positive negative. Actually, would that make the first term negative? We'd have to do like an n. No, that'd be okay. I'm not sure if we should probably put an n plus 1. I'm not sure. A 50-50 shot. So you basically flipping it every time and then times it by 3 and then the previous answer. All right. Write an expression for the nth term of sequence. Okay, so this is a recursive definition. So an expression would be basically do this without recursion. So I can write the pattern for the nth term. So a sub n. So notice the nth term. If we have a pattern going on here, we're still doing that -1. We're just trying to find the nth term of sequence. So it's going to be a -1. And notice like all the even numbers of this n equals 1, 2, 3, 4 are negative. So it's actually going to be an n plus 1 pattern that would make all the evens negative. And then it's going to take a certain number. And so there's going to also be like, you're timesing by 3. Huh. It's kind of a difficult problem there. And so if you're sitting there thinking about it, you're like, huh. So this is one of those things that you kind of have to look at the pattern. And some of this you have to like go back to your old things that you learned in the past. So we go in our way back machine to algebra 2. And the actual pattern is going to be times 2 times 3 to the, we can say n plus 1, n minus 1 power. And this would actually make it work. All right. Because it's times 2, but when we still have that like 3 to whatever power because we're multiplying by 3. So this would be a valid formula for that pattern. All right, moving on. So convergence or divergence. So a series can either converge or diverge. We talked about divergence. That means it's going to infinity, positive or negative. When a series converges, it goes to a number. So a series is a sum. You're adding all the numbers up. As you keep adding, and this is when you go to infinity. So if you keep going on forever, is it going to approach a number when you add everything up? Or does it just keep growing forever or keep shrinking forever? And that's the question. This is going to be a big part of calculus. So let's look at this. Let's find the limit of this sequence. So basically to find if a series converges or diverges, we have to find the limit of the sequence. So the limit as your n goes to infinity, I want to find if the sequence of numbers converges or diverges. Did I say series? This should have been sequence, I think. Oh, what a terrible video. N over 1 minus 2 to the n. If you use L'Hopital's rule, this would be infinity over infinity, so we have to derive, right? So when you derive it, it's going to be 1 over -2. And limit as n goes to infinity. And that means that limit is -1/2. So yes, it converges to the number -1/2. If n grows to infinity, these numbers, it's going to approach the number, the sequence. That means the last term, as you go to infinity, is approaching -1/2. So let's look at this. If the limit does not exist, that means it's going diverges. Then the sequence, yeah, exactly. If the limit does not exist, then it does not have a limit. We say it diverges. That means it's going to infinities. So to determine if these sequences converge or diverge. When you're looking at this sequence here, let's look at this pattern, -1 to the n power. That's going to be 3 plus -1 to the n. Now, as you keep growing, this is going to be either -1 or +1. It's going to rotate between the two. So our pattern is going to be like, it's going to start, let's say n equals 1. It'll start at 3 minus 1 is 2. And then it'll be 3 plus 1 is 4. and it goes 2 and 4 and 2 and 4. Notice it's going back and forth all the time. It's not actually converging on any number. I know it's like staying within that range, but that's not what we're looking for. So we say this pattern diverges because it's just rotating. It's not actually going to infinity. It's one of those cases it's just rotating between numbers. Now let's check this one. Okay, so again, we have to check the limit as n approaches infinity of ln of n squared over n. Okay, so I'm going to use some of my log math here. I'm going to rewrite this. I don't want to say ln of n squared. I'm going to put the 2 on the outside. And again, if you put infinity, you get infinity over infinity, which is L'Hopital's rule. So we got to derive this. Derivative of 2 ln of n is going to be 2 over n. And then it's going to be over n. 2 over n, oh wait, and that's going to be 1 when you derive that. So it's just 2 over n. And again, the limit as n goes to infinity, which is going to be 2 over infinity, which is 0. So yes, it converges to 0. It's always going to converge to a number. Okay, so the concept, 2 vocab words, monotonic, where it's non-increasing or non-decreasing, which is the way of saying that. It's always going up or it's always going down. It's always growing or always shrinking. It's not like rotating back and forth. Or it's always staying the same. Okay? Like monotone. It's not up and down. Bounded, so sometimes we have this concept of bounded, and that means our sequence has an upper and lower limits. So that means like this, there's a minimum number and a maximum number. So let's look at the sequence 1, 2, 3, 4, and 5. If you keep growing by 1, well, we know the lower limit is going to be 1. What is the upper? There is no upper limit because it keeps growing forever. So we can say this one is only bounded on the low end, or we'd say it's unbounded because it's not bounded on both. But let's look at this pattern. So the lowest number you'll see in this pattern is, well, 1/2, 1/4, 1/8. You're multiplying by 2. So technically the upper limit is 1/2, but as you keep shrinking, it gets smaller and smaller and smaller. The number on the bottom keeps doubling. Well, this is basically going to be going to one of those 1 over infinity. The lower limit is going to be 0 because it's never going to get it's never going to reach 0. It's just going to get really, really small. It's like 1 over infinity. But it's never going to get to negative. So this is a bounded sequence. This one is not because the upper keeps growing forever. So let's look at some examples, determine whether these sequences are monotonic or bounded. So again, this one, when you're rotating up and down, again, this is like going 2 to 4 to 2 to 4. It's not monotonic because it's increasing, decreasing. So not monotonic, but is it bounded? Yeah, it is definitely bounded because it's just going between 2 and 4. Those are the bounds. Now let's check this one. 2n. So what you might want to do is write down the first few numbers of a sequence. So to be n equals 1 will be 2 over 1 plus 1, 2 over 2. And n equals 2 would be 4 over 3. And then 6 over, this is n equals 3 over 4. And then times 2, 8 over 5. Times 2, 10 over 6. And so on. So now our number is 1, and then it's growing a little. 4/3, and then this grows up to 3/2, a little bit bigger, 8/5, 10/6. It's actually slightly growing. Okay, so it actually is monotonic so this is definitely monotonic because it's growing slightly all the time. It's not going to start shrinking. And is it bounded? Well, the number's always going to get 1 is going to be the lowest number. And the biggest number, what's the biggest number? Well, this is the idea if you go to the limit as you go to infinity. And limit of 2n over n, this is L'Hopital's rule, will actually be 2. So yes, it is bounded because it's bounded between 1 and 2. All right, we're going to save some of those for later. And we're done.